Yeah, good morning, everybody. Yeah, the participants are still joining here. We'll be starting shortly. Yeah, we shall start in a while. There are just 27 participants. I'm waiting for some more participants to join me. Okay, we'll be starting shortly. Okay. So in the last class, we were looking at the Z transforms of infinite amplitude. Z transform infinite sequences. So we have seen the different types of infinite sequences. Yeah. So yesterday we were just looking at these Z transforms. Okay. The Z trans. I'll just recall till the others join us. The Z transforms. What for Z transforms are being used? The Z transforms are being used. I hope the audibility is good there.
Sir.
Yes. Tell me.
Yes,
Sir.
sir.
You're able to listen to
Yes,
me,
sir.
right? Okay. Good. I'm muting you all. Okay. So that there's not be any disturbances. I'm muting you all. Yeah. So let's start with the session. Yeah. The Z transforms are for discrete time, whereas the Laplace transforms are for continuous time. We have seen that. Okay. So this is defined by this particular equation, right? And this particular equation is called as a bilateral equation. Okay. Because we are starting from minus infinity to plus infinity, and x of z and x of n are called as the Z transform pairs. Okay, so this is just what we had seen yesterday. Okay, this is two-sided. Since it is from minus infinity to plus infinity, it's two-sided transform. Similarly, there is another transform which is from 0 to infinity. This is unilateral or one-sided. Okay, region of convergence also we saw yesterday. Okay, and what is that region of convergence telling us? The values of z, which makes x of z finite. Okay, listen to me once again. What is region of convergence? Region of convergence of values of z. Region of convergence involves all the values of z, okay, that will make x of z a finite entity. That means it should be a bounded entity. For what values of z it would be bounded? So those values of z would form the region of convergence. Okay, so that is what we had seen. And we also discussed there are three types of finite duration sequences. One is right-sided sequence. It will only be there from 0 to infinity. Okay, they are also called as causal sequences. Okay, and we also saw there is something called as left-sided sequence, and the left-sided sequence ranges from minus infinity to zero. It's a left-sided, minus infinity to zero. This is right-sided, zero to infinity, and there is one more that is double-sided, both left side as well as right side. That means it can range from minus infinity to plus infinity. So this is the right side is from zero to infinity, the left sided is from minus infinity to zero, and the double sided could be from minus infinity to plus infinity. But we are, since we are finding the, we are considering the finite durations. Okay, uh, we'll be considering this. We also have seen this yesterday. Why this is called as right sided sequence? See, it is starting at zero. Okay, and it is going on to the right hand side. Okay, and it is finite. Since it is finite, it has got just four samples. It is starting at zero and it is going till one. Okay, now if we try obtain the z transform for this, we consider this equation to begin with, which says n ranges from minus infinity to plus infinity. Okay, but any problems there? No, right? The you're able to listen. Yes, no problem. Yeah. Uh, though it ranges from 0 to 3, we start by this equation which says minus infinity to plus infinity, but next we write that equation. Since it is moving from 0 to 3, okay, we change these limits from 0 to 3. Okay, this is how it looks. Okay, and since this is finite duration sequence, there are four samples. Okay, bring those four samples here. X of n, in place of x of n, we can have x of 0 to the power z to the power 0 plus, because the summation is there. Then x of 1 into z to the power minus 1. So like that. Okay. And in this place, x of 0, x of 1, x of 2, x of 3, just place these. It looks like this. Okay. So we have found out the x of z, but I have told you in z transforms, whenever you find the z transform of a sequence means understand it's a discrete signal. Okay, discrete signals are also referred to as sequences, but the continuous time signals are not referred to as sequences. Understand that only the discrete signals are referred to as sequences. See, this is sequence of numbers, they're all samples, right? That's why it is also called as sequence. Okay, so what we have done now is we have found out the z transform of this finite duration sequence, which is right sided. Okay, and see, now we have to find out the ROC. Every time we find out the z transform, we should not forget to find out ROC. What is ROC? As I told you, ROC is the values of z which will make x of z finite. Okay, values of z which will make x of z a finite entity. So in other words, what values of z would make x of z infinite? We shall see. When would this x of z be infinite? For what values of z this would be infinite? We shall see. And except that, all other values will make this finite, and that would form the region of convergence. Okay. Now, since there is z inverse z minus 2, z to the power minus 3, all these z's would come in the denominator. It is 1 by z, this is 1 by z square, this is 1 by z cube. I'm just recalling what we have seen yesterday. Okay, so we have not still started with the today's problem. Okay, I'm just recalling what we have done yesterday. It's 2 by z, it's 2 by z square, it's 2 by z cube. Okay, so for what values of z, x of z would be infinite? Since z's are in the denominator, you substitute z as 0. So z equal to 0 would make this x of z infinite. See here, if z is 0, x of z would be infinite. Okay. Similarly, uh, if z is equal to 0, this is being infinite, except this, except z is equal to 0, all other values of z would make x of z finite. At z equal to 0, x of z would be infinite. Okay. When would this be finite then? Except z is equal to 0, for all other values of z, it would be finite. So the values of z which would make this finite would form the region of convergence here. Therefore, the region of convergence is entire z plane. Entire z plane means all the values of z. Entire z plane means all the values of z except z equal to 0. So how to denote that symbolically? Like this. Okay, so z magnitude means except z equal to 0, all positive values of z and all negative values of z would form region of convergence, because for those values of z, x of z would converge, or it would be a finite entity. So for right hand sided signals, what we should understand, for right hand sided sequence, the ROC is entire z plane except z equal to 0. Now if we take left sided sequence, say this is left sided sequence, what's happening here? This is the zeroth sample. This is zeroth sample. So this is at n equal to -1, at n equal to -2, at n equal to -3. In the previous case, this is 0, 1, 2, 3. In this case, it is 0, -1, -2, -3. So what is the range? Range is 3 to -3 to, sorry. It's from -3 to 0. Okay. So this is the equation we use to find out the Z transform. This is the range is from -3 to 0. The limits will change now. Yes. Since the limits will change, bring those limits here. This is how the equation would look like. Okay, in place of x of n, bring x of -3, z to the power minus of -3, that would become +3. Then in place of this, you bring x of -2, z to the power of -2, that will make it z square. Okay, bring x of -1, z to the power of -1 would become, okay, this is how the equation would look like. Then in the next case, all these samples need to be substituted. X of -3 is 1, x of -2 is 1, x of -1 is 2, then x of 0 is also 2. This is how these Z transforms look like. Similarly, similar to what we had done in the previous case, let's see for what values of Z this x of Z would be infinite. What values of Z would make this infinite? For z equal to infinity, this would be infinite, right? For z equal to infinity, this would be infinite. This will not form the region of convergence. Okay, for what values of z, x of z would be finite, that would form the region of convergence. But at z equal to infinity, it is infinite. So z equal to infinity is not a part of region of convergence. Okay, so if z equal to infinity, for z equal to infinity, if it is getting infinite, except this, for all other values of z, it would be a finite entity. Okay, so this means that x of z is finite for all values of z except z equal to infinity. Except why z, except z equal to infinity? Why? Because at z equal to infinity, x of z is infinity. So leave that. Leaving that, all other values of z would form ROC. So that is what this is. Therefore, ROC is entire z plane except z equal to infinity. How to represent that? This is how we represent. Except, this magnitude tells that except z equal to minus infinity and z equal to plus infinity, rest all the values of z would make ROC, the region of convergence. Okay, what is the region of convergence? The values of z for which x of z is finite. Okay, for what values of z, x of z is infinite, leave that. Rest of the values form the ROC. Okay, so this is where we had stopped in the last class. Okay, and there is one more, that is double-sided sequence. So we have, till now we have seen the left-sided sequence, right-sided sequence. For right-sided sequence, the ROC is entire z plane except z equal to 0. For left-sided sequence, it is ROC is the entire z plane except z equal to infinity. So what is it going to be here for double-sided? Why it is called as double-sided first? What is called as double-sided? See, zeroth sample is here. Okay, and to the right hand side also we have the samples, to the left hand side also we have the samples. That is why it is called as double sided. So this double sided sequence is the combination of right sided sequence and as well as left sided sequence. That is why it is called as double sided sequence. So what is the range? What is the range? If this is the zeroth sample, okay, the range is from, this is 0, -1, -2. Okay, so it's from -2 for n equal to -2 to +1 is what is the range of this. So how to find out the Z transform? You will consider the same equation. Is the same equation everywhere to find out the Z transform. Okay. So what is the range now? Range is -2 to -1. That is what we discussed. -2 to -1. The positive values of n are also there. The negative values of n are also there. That's why it is called double-sided. So how does this equation look like now? This equation, the values of the summation are interchanged. It is -2 to 1, -2 to 1. Understand that? Double-sided sequence, both left-sided and right-sided, starts at -2. How? This is 0 means this is -1, this is -2 samples. Okay, so -2 to 1. That's why the limits of summation is adjusted to be this. While taking, we take it from -infinity to +infinity because this is the standard equation. In this standard equation, seeing the x of n, we will adjust that. Okay. Now, how does it look like? Just substitute. Just substitute. If you have got your books, can you just proceed from here on a step further from this? Can everybody try that? I hope everybody is having a notebook and a pen. So from here on, from whatever we have seen in the previous two examples, from that experience, can you just try extend this for further two steps? Just expand the summation. Everybody do that, please. There are just 39 participants. The participants are less today. What is that? Yeah. Keep doing that, everybody. Just extend this. Just keep this as a reference and extend this. Expand this summation, I mean. I hope everybody is doing that. Okay, keep this as a reference. Okay, this is x of -2, x of -1, x of 0, and this is x of 1. Okay, done that, everybody? Now, see, I hope you have finished, and this is how it should be looking like. Okay, see here, see the powers of z. You have positive powers of z as well as negative powers of z. Where you used to have this positive powers of z for left-sided samples, you'll have positive powers of z because it is z to the power minus of -2. It is z to the power minus of -1. That's why for left-sided samples, you'll have the positive powers of z. For right-sided samples, you'll have negative powers of z because it is z to the power -1. Minus n is there. N is 1 for this. So it is -1. So this is the right-sided sample. This is the left-sided sample. Now you have right-sided as well as left-sided. Okay. So now think, and just we'll go one more step further and just substitute this x of -2, x of -1, x of 0, and x of 1. Okay, after substituting these samples, okay, these samples here, this would look like this. Okay, now let's understand the same scenario. What is that? For what values of this is after finding out x of z, we need to be finding out the ROC. Okay, so how to find out ROC? This is x of z. For what values of z, this x of z would be a finite value. To understand that, to just see for what values of z they are, this x of z is infinite. See, if you consider these two values, when z is equal to infinity, x of z is infinite. If you consider these two values, and if you consider this value, when this z inverse means it's 1 by z. So when z is 0, this z, when it is 0, this will make it infinity. When these z's are infinite, they will make x of z infinite. That means for z equal to infinity also, this x of z would be infinity. For z equal to 0 also, this x of z would be infinity. So leaving those values, leaving z equal to 0 and leaving z equal to infinity, rest all the values would form the infinite, would form the ROC. Okay, so that is what is written here. The x of z is finite for both z equal to 0 and z equal to infinity. Why it is for both z equal to 0 and z equal to infinity? Here it is z equal to 0, which will make this infinite. Okay, here it is z equal to infinite, which would make this infinite. That's why x of z is infinite for z is equal to 0 as well for z equal to infinity, which was not the case in left-sided and right-sided sequence. In left-sided sequence, when z is infinity, x of z is infinity. In right-sided sequence, when z is 0, it would be infinity. But it is, since it is double-sided, we consider both the values. Okay, so which means that x of z is finite for all values of z except z equal to 0 and z equal to infinity, because at z equal to 0 and z equal to infinity, x of z is becoming infinity. So except those two values, all other values of z would make x of z finite. So what is ROC then? Therefore, ROC is entire z plane except z equal to 0 and z equal to infinity. So how is that denoted here? Except z equal to 0 and z equal to minus infinity and plus infinity, all values of z would form ROC. So what we have seen till now is we have found out the z transform of the finite sequences, z transform of finite sequences. How many types of finite sequences we have seen? We have seen three types of finite equations, which are finite sequences rather. Which are those? Right-sided sequence, left-sided sequence, then double-sided sequence. We have found out the Z transform for all these sequences, and also we have found out the region of convergence. Remember, I'm telling you again, for any sequence, if you find x of z, that is the Z transform, for all those you have to be finding out the region of convergence. So without finding the region of convergence, the solution is incomplete. Okay, remember that. Okay, now after seeing the finite sequences, okay, we shall go for seeing the Z transforms of infinite sequences. Okay, infinite sequences means they are infinite in length. Till now we have seen three sequences, three types of sequences. They were all finite in length. We were considering four samples everywhere. See here, four samples are there. Okay, only with four samples we dealt with, because we are dealing with finite sequences. We were dealing with. Now from here on, we are dealing with the Z transforms and ROC of infinite duration signals or sequences. You can call them as signals or sequences. Your wish. Yeah. So the first standard signal, you can call them as standard signals. Okay, we were looking at U of n, right? It's a standard signal. Then we were looking at delta of n, which is a standard signal. Then ramp we were seeing sinusoidal signals. They're all standard signals, right? So it's a combination of such standard signals, which is positive time exponential. If you just leave this U of n, if you just leave this U of n and see this a par n, okay, what type of signal is this? What type of signal is this? This is a real exponential, see, exponential signal. Okay, and u of n, what does this mean? U of n means, u of n means this a par n exists from 0 to infinity. So since u of n is another function of n, since u of n is another function of n, we can say that. So the network at my place is bad. If often disconnects me and connects me back again, because man, it's okay, okay. But be there, and if you're able to listen to at least, okay, keep listening. Let's not get away from it. Fine. Yeah, x of n is equal to a par n u of n. So this is a positive time exponential. And why this is infinite duration? Because u of n is there. U of n very clearly says that it ranges from 0 to infinity. So in that sense, they have considered this as a infinite duration sequence. Okay, so for this particular sequence, if we apply the Z transform, how would it look like? And what would be the region of convergence for this particular Z transform? Fine, let's go on now. Just a sec. Yeah, so this is what we were going on with. Again, we have considered the same equation. Okay, this equation is standard everywhere. Whether you find the Z transform of the finite duration sequences or infinite duration sequences, this particular equation is what you're starting with. Okay. Now, in place of x of n, you will have a power n u of n because x of n is given. It's not a finite sequence. There we had 1, 1, 2, 2 sort of a sequence where we had just 4 samples. So it's not a question of 4 samples. There are infinite number of samples. Okay. So how to deal with those infinite number of samples need to be learned here. Okay. So what we're doing, we have uh, x of n in this place. Okay, so in this place x of n needs to be brought in, so which is given as a power n u of n. So in the next step, that is what is being done. So in this next place, a of n, u of n should have been there. And why u of n is not there? Because u of n is 0 for n less than 0, or it is 1 for 0 to infinity. Since u of n would come here, and since u of n is 1 for 0 to infinity, so what we do is this. Okay, then see here, then we have this. So this, how does this look like? If you take this n out, a z inverse would be within the bracket and this n would come on. And always you should express in the terms of something to the power n. Okay, so to the power n, power should be n, it should not be minus n. So try express your summation always in this particular format because it's a standard summation. So if you get to the standard summation, okay, it would be easier to write the result of summation. Otherwise we'll not be able to, because it's not a finite sequence wherein we can write, okay, x of 0 z to the power 0 plus x of 1 z to the power minus 1 plus x of 2 z to the power minus. No, we cannot write that because there are infinite such sequences. Okay, so when we are dealing with infinite sequences, you need to arrange this properly. 0 to infinity is what we need to be there. Why it is from 0 to infinity? Because u of n is there. U of n should have been there here, but u of n is substituted as 1, and after substituting u of n as 1 here, okay, so it is made 0 to infinity. Earlier it was minus infinity. This is minus infinity to 0. It's not seen properly here. It's minus infinity to 0. Okay, so from minus infinity to 0, it is minus 1, it is 0, which is 0. U of n is 0. So u of n is 1 from 0 to infinity. That's why this is 1 and this becomes 0 to infinity. And if you rearrange this, taking this n outside the bracket, okay, why this should be expressed in this particular form? Okay, the reason is this. See here, this is the standard summation. This is a standard summation. You need to remember this. Okay, so unless you know this standard summation, it would not be possible to solve this particular summation. You cannot just say it's a power z inverse to the power 0 plus a into z to the power minus 1 to the power minus 1. No, you cannot do that. Okay, so what is best here? What is best here is to understand the standard summation. See, this is in the form of the standard summation. The summation is going from 0 to infinity. This also is going from 0 to infinity. It is something to the power n. That means in place of a, you have a z inverse here. So this is a. So in this, we have in this standard summation, we have a. Okay. Now I'm left with 10 more minutes. Okay. Let's see this. Let's not bother about the time. Let's understand this, because if you understand these initial sequences and the Z transforms, it will be much easier. It's all about rearranging this in a standard way. Okay, so how to rearrange that? Bring this into the standard form, and if you bring this into standard form, the summation would be 1 by 1 minus a. When is it possible? This is possible if a is less than 1. Since this a Z inverse, this would be less than 1. Okay, this would be less than 1. Since this a is less than 1, this a is less than, I can express this as 1 by 1 minus a. So this is the standard summations. Okay, so how should this be looking like now? Just tell me, with reference to this standard summation, how should this be looking like? It should, this is a. In place of a, you bring a Z inverse. That means 1 by 1 minus a Z inverse is what it looks like. Okay, 1 by 1 minus a Z inverse. Okay, so if you rearrange this, it will become Z by Z minus a. So you take this a by Z inverse, a Z inverse is right there, right? You make it a by Z, take the LCM, it will become Z minus a, and the denominator will have Z, right? Take that to the numerator, it looks like Z by Z minus a. How did they write this ROC? Okay, so this needs to be understood. Fine, that is what is our next task. How did you bring this ROC as Z greater than A? See here, for above X of Z, how to find ROC? They already have given us ROC Z greater than A. How is that Z greater than A? Remember here, whenever we are trying to find out the ROC, I have told you, every time you find out X of Z, you have to find out ROC. Okay, so they have found out the ROC and given that as Z greater than A. Everything that is greater than A. Okay, A will take many values. I'll be talking about that. Fine. So how to find out your ROC is this. Always don't consider the equation where you find Z's, but consider the equation where you find Z inverse. It's the fund of that, fundamentals rather. Okay, don't forget to consider the equation where you have Z inverse. This again we have expressed in terms of Z, but when you are finding the ROC, don't consider this final equation. Consider the equation wherein you have Z inverse. Okay, so how does it look like? In the above equation, x of z would converge or be finite when would this be? When would x of z would be a finite entity? Just don't see this now, because we are talking about ROC. When we are talking about ROC, we are not seeing this. We are interested in this, where z inverse is there, not where z is there. Okay. So what we do here, for this x of z to be a finite entity, what should be done here? Okay, if this is 0, what happens? If this 1 minus a z inverse, 1 by 0 is what? Infinity. So x of z would be infinity. That will not help me find out ROC. What is ROC? ROC is something, for ROC is set of z, set of values of z, which will make this finite. So for this to be finite, I can say this denominator has to be a number greater than 0, or say magnitude of this denominator has to be greater than 0. It should never be 0. If this is 0, what happens? This will become infinity, and that will not help us find out ROC. What will help us find out ROC? If this magnitude is greater than 0, then this would not be a infinite entity. This would be a finite entity when the magnitude of the denominator is greater than 0. That is what is being told here. See, if 1 minus magnitude of 1 minus az inverse is greater than 0, then it would be a finite entity. That's why we've considered this. So the same thing can be expressed as this. How? You can send this az inverse to the right. How it would look? It would look like 1 is greater than az inverse. 1 is greater than az inverse is similar to az inverse is less than 1. Anyways, okay, you take this az inverse to the right. You can read that as 1 is greater than az inverse, which also implies that az inverse is less than 1. Okay, now you take this z inverse as 1 by z. Okay, and see, if you do that, this z will come here, so it's a less than z, or you can say z is greater than a. Everybody understand this point? How did this ROC becomes z greater than a? Okay, because of this reason. How to find out this? Don't see that here. Okay, always see that here. For this to be finite, this, the magnitude of this has to be greater than 0. If it is greater than 0, you will see that z is greater than a. So ROC is z greater than a. Now we need to sketch this ROC. We didn't sketch these ROCs in finite sequences because we were talking about entire Z plane. We don't talk about entire Z plane here. Remember, there in finite sequences, if it is left-sided, it is entire Z plane except Z equal to infinity. If it is right-sided, it is entire Z plane except Z equal to 0. If it is right-sided as well as left-sided, if it is double-sided, then it is z equal, except z equal to 0 and except z equal to infinity, entire z plane. So in all the three cases we were saying entire z plane, entire z plane, and entire z plane. So it was difficult to sketch the ROC there. That's why we didn't sketch that. Okay, but here we should try sketching them. Okay, now if you have to understand the sketch, okay, understanding this would become very easy. Just make this slide very clear to you now. Okay, because this is something that will help you plot that graph of ROC. Now you have found out your x of z to be this. See here our x of z is this now. For sketching the ROC, this will help. For finding the ROC, this will help. So for sketching the ROC, we are considering the final equation. Okay, see, this is what we have considered. Now let's understand this. There are something called as zeros and poles we need to understand if you have to sketch the ROC. Okay, zeros and poles. What are zeros? Zeros are the values of z which will make x of z 0. That means for what values of z, x of z would be 0 here? Can you tell me? For what values of z, x of z is 0? For z equal to a, what is x of z? For z equal to a means it's, if z is a, it's a minus a. That means it is a by 0. It would be infinity. But for this to be 0, z has to be a 0. Okay. So how many zeros are there? X of z. When would this x of z would get 0? If z is equal to 0, x of z is would get 0. So 1 0 will exist at z equal to 0. What is 0? What is called as 0? There are two entities, zeros and poles. Zeros are represented by O, poles are represented by X. Okay, how many zeros are there? There is just 1 0, which says that if z is equal to 0, x of z is 0. Okay, similarly, the values of z which would make x of z infinity are called as poles. So how many such values are there which can make x of z infinity? See here, when would this get infinite? If this denominator is 0, then this would get infinity. So for what values of z this denominator can be a 0? For z is equal to a, this denominator can be what? 0. So if denominator is 0, x of z would be infinite. Understand? Okay, I have less than 1 minute now. Let's stop here. Okay, again in the next class I'll start with poles and zeros. I've still not plotted that. I've still not plotted. Okay, I'll plot that, and I'll explain you again what are zeros and poles more clearly rather. Okay, as of now I think we can stop. If something is there, rather we can take this. Any, yeah, I'm uh, I'm unmuted. You can. I think you can talk. I'm unmuted. Yeah. I'll again mute all. Okay, you can unmute yourself and you can talk if you have something.